Okay, that was super interesting, looking at logistics. Interestingly, we'll stay at logistics for another talk now. We'll look into traffic management. Especially, we'll look into a harbor, like a harbor environment. So we go to the sea if you want. And with me today, I have Dr. Fritz Schinkel, who is head of quantum solution of the quantum solution team at Fujitsu. And he'll talk about quantum-inspired traffic light optimization. Mr. Schinkel, Dr. Schinkel, thank you so much for being here. The floor is yours.
Yeah, thank you very much for inviting me and having me here today. I very much appreciate it. Very warm welcome to all participants of the conference. What I want to do in the next 20 minutes, tell you a little bit about a use case that is possible today with quantum-inspired optimization in traffic management. And yeah, this is a project that we did at Hamburg Harbor, the Hamburg Port Authority, responsible for the harbor area, and they are running not only the water side, they're also running the land side, and it is not a very tiny, but a really respectful network. It has to carry over 20,000 trucks per day. It has 35 traffic light controlled intersections and over 100 kilometers of lanes between them. And it is something that is under steady change and needs to adapt and have good performance for the demands. And they already have some problems, of course, with congestions. They see the problems with carbon emission and things like that. And they don't have much room to construct new routes here. As you can see, so there's a lot of water around it. And so the question is, how can that be done with the infrastructure that is in place, with more smart management of the infrastructure? And currently they are using this local actuated traffic light controls on each intersection. And they see that they have problems with that to grow anymore. And the question is, can we do something more globally with means of new computational chances as in quantum computing? So, but first let's start, what does it mean locally actuated? That means we have a monitoring of each crossing, and it's checked if there are no cars, few cars, or a lot of cars in front of a traffic light. And yeah, the natural reaction then is give those more green where you have more cars. A rule-based system. This is improved somehow with artificial intelligence in the recent time, and that helps perhaps a little bit. But what it stays, this extension and truncation of green decisions, it's a local decision. It does not take into account the next road, the next intersection, or global effects. And the question is, perhaps, is there potential, and could we get that? And what we also see with these local policies is that under heavy load, they converge to fixed time behavior. Of course, when you have in every direction a full observation area, then what is the reaction? It's always the same reaction. And yeah, so the question is there potential, and how can we lift that? And so we went here from this rule-based local behavior more to an observation, a test, a look, what if, and a global view of that. And how did we do that? So first we look locally again, but we don't look to intersections, we look to roads. And the roads are mostly influenced by the traffic lights upstream and downstream. So we have their control programs with longer or shorter green for that particular direction. So we can reduce the inflow or we can reduce the outflow or increase it. And now we can look in these scenarios for different alternatives on the respective intersection, and can simulate and predict what will be the quality. And quality here in our case is average speed of all the cars in that road. And yeah, once we have predicted all these combinations, we can stitch them together to a global view of our prediction. So if we now have decisions for each intersection for a certain program, we don't have to recalculate the complete map again. We can simply take our local predictions here for the specific pair that we see here and say, then we have the colleague contribution that on all these roads, and can calculate a global quality from these local predictions. So once we've done that, we only have to take now all the possibilities and find the best one. So that's our task now. And the pity of that is we can't look through that huge pile, of course. If you take into account that we have 35 intersections here in the harbor area, that would mean to synthesize and look into 10 to the power of 35 different structures. And that's, of course, nothing that we can do in real time. Even we can't do that in real time for our universe, but at least not in real time for traffic, which is a subject of seconds. So we have to find a smart way to do that, and quantum computing, as you will see, will help here. So what do we have to do? We have to be ready in 10 seconds. So that is a demand from the traffic side. You observe something, and if your reaction still should have some effect, then it must start not later than 10 seconds. And the computing side could get 5 of them. The other 5 are for the network side to roll it out to the traffic light controllers in the area. So how can we do that? First, we have these simulations. We use here microscopic simulation, cellular automaton. Nagel Schreckenberg, for experts, is a inventor, 2 professors from Germany who use cellular automaton to simulate traffic, and we had to improve this a little bit for this urban situation here. And we could do with this for our proof of concept here, where we had 5 intersections on a normal PC in less than 3 seconds. So this is something that takes at the moment the most part of it. It could be even accelerated, and if we grow, it can easily be parallelized. These predictions are completely independent, so it can be done on different machines if you need it for tens or hundreds or even thousands of roads. So that part takes 3 seconds. Then we have to go from the local view to the global view. Here we see a brief view on our optimization model. It's such an so-called QUBO, quadratic unconstrained binary optimization. And we have here 2 decisions for programs in 2 intersections, the from and the to intersection. And for each of these decisions, we import here the predicted quality for these decisions on this particular road. And yeah, then if we have a certain setting of variables for a decision which program is taken, then we have here the sum of all qualities. So this is something that nicely sums up in this quadratic unconstrained binary optimization. And the other term here is a technical term to make sure that exactly one program is chosen for each intersection. Of course, that's a logical constraint that has to be followed all the time. So bringing this together is also not a big task, and it's easily possible in less than a second. And then it leaves a second for a purpose-built hardware that can solve, that is specialized in solving such kinds of problems. So that can do now the job for us to find the best or even a very, very good solution from that huge pile of possibilities that we have built in this energy model here. And so we can react with a very good answer. So that was a little bit too fast. So you see, we are ready here in 5 seconds. Even it can be improved. But there is no obstacle from the compute side to use that model. And yeah, now we have to see what are the benefits of doing this. So we rolled it out on the harbor network here, 5 intersections in this proof of concepts. It's about 20 kilometers of lanes between those. And we measured all possible routes from every entry to every exit. So those are 72 routes. And the load was a load of about 4,000 vehicles per hour here in that scenario that we measured. What we see here is a visualization from our cellular automaton. We also see this here a little bit, and you can you can see that it's not a pure cellular automation where each cell means there is a vehicle. We cover here more than one cell with a vehicle for the longer trucks and things, and we have also tweaked it with floating point accelerations and things like that to make it more appropriate for this landscape. And yeah, now it works pretty good as a prediction simulation for our optimization. And we take this for these typical scenarios between two intersections and do all our predictions in time based on that technology. So this is internal view, and now we have to prove externally what we can reach. And for that, we, of course, took not our own simulation as a self-fulfilling prophecy. We took well-accepted traffic traffic simulation tool from PTV, the tool Vism, that can do high-precision simulations of vehicle traffic on networks. We did build that network again in that technology. We used as data the historical data, typical morning and evening peak in that area, and the very interesting noon peak, which is with a lot of trucks, and that is the most interesting one for the economical behavior of the harbor area, that this is not congested. We took as lead index, as a key performance indicator, the average speed to compare the scenarios, and we compared fixed time programs and then these locally actuated policies that are in place today with our new concept of traffic light optimization by this global view. And first result you can see here. We have here the average speed over time. So we have here a burn in. First, the network is empty. Cars are driving into it with a limitation of 50 kilometers or a little bit like that. Of course, it then slows down because the network is filling, and after a burn-in phase here, after 5 minutes, we switched on then the optimizations. So in the first, or the two curves are over another, but then you see they split, and yeah, you can see the pink curve from the fixed time program is going down here a little bit, while the optimized curve even goes up a little bit in this scenario. And this is with 100% load. And if we have more load on that, the gap even widens a little bit. So we already can see here the effect. But of course, we want to know how much is this, what in more tangible terms, what is the improvement that we can reach here. And therefore we compared the travel time savings in average. So what in average each participant of the traffic can save here in time in the different scenarios. And you see here what we did in the noon load. We started with 100% historical data, and then we did increase the load by 110%, 120%, etc., by letting flow in more cars from each direction, and see how the network responds with the different control mechanisms. And you can see all the three here. Blue is a fixed time program, the locally actuated is in orange, and the global optimization in green. They could respond here to that, so it was possible to send more traffic into that network. It was not already saturated. 170% it starts here. So a little advantage, a little bit more with the green curve, but the real benefit you can see here from the lower chart, where we have the travel time savings now. And even in the normal case, there are savings, about 5% savings. Everything is working a little bit faster by reacting with a global view to the unforeseeable things, trucks, etc., coming. And when the load goes higher, then we see that the locally actuated is not only limited, it even is counterproductive sometimes, and has some random results, while a global view can still have a very good beneficial decision over the whole network, and we get here travel time savings of more than 20%. The second question here was carbon dioxide, and we also could take a look on that. We had that in the data. So from the movement data from the vehicles, we could calculate the acceleration parts of that motions, the work in there. That's where the energy is consumed, where the carbon dioxide is produced at most. And so we see here in the different policies how we can influence that. So with the locally actuated, there are also some improvements, but much more improvements with a global view, up to more than 9% savings compared to the fixed time program for these scenarios. So that's what already also was known from scientific traffic engineering research, that the average speed is a key indicator that leads also other indicators positively, though we don't have directly optimized here for carbon dioxide. Perhaps a direct optimization could bring a little bit more, but also here is a positive effect already in. Yeah, so these are the results that we could do for the situation. Let me sum up what we've done. We've changed this local view that is done mostly today, and we could show that it is possible to do that. It's a hard computational task to do it, and it was not possible without quantum inspiration, so to say. And the results, possible lifts are really promising. So over 20% in the travel times and 9% in the carbon footprint. That is really good figures that we see here. It's a scalable thing, so we can scale out the prediction machinery, and the decision chip from the digital annealer from Fujitsu with 8,000 bit would be capable for about 1,000 intersections. So there's also really room for growth. Yeah, and the thing is now very promising on very credible simulation. So the next step will be to go into the physical world with that. And that's it. So we have perhaps a minute for questions.
Dr. Schinkel, thank you so much. Indeed, we have a minute for questions. Question from the audience to you. I think this is an interesting one. Different car speeds with a lot of cars normally lead to traffic jams, right? According to chaos theory. How do you take that into consideration when you use the average speed to optimize? That was a question by the audience.
Okay, yeah. The average speed was not a hyperparameter that we optimized directly. That was something that we summed up in the predicted or simulated situation. We simulated the traffic as it is with all the individual possibilities there, with the stopping characteristics of trucks and normal vehicles, etc. And from that, we took as a number for our numerical optimization, then the average speed of each such situation. So there was not a direct optimization of average speed. And well, by that, we could take these results and, as I've shown, combine them to a global optimization function, which very much which is very, very good covered by a quadratic model for annealing here.
Okay, got it. Thank you so much for the explanation. Wonderful. Dr. Schinkel, thank you so much for being with us today. Thanks for your talk. I wish you a great rest of the conference. And again, see you soon. Thank you so much.
I thank you. And have a look at our booth if you have more questions. And yeah, more reading materials here. Thank you very much for having me. Bye-bye.
Bye-bye. Thank you.